let's think about what these things imply. So the value of a state, well, under the Bellman equation is this, and, nothing scary here, right? This is all stuff that you know.
Yeah.
So now the next thing we're going to do is we're going to say, well, the value of the state that we end up in, since we're in averager land, we can write that as the sum over all the anchor points of how related this state S prime is, or what the weight is between S prime and that basis point, and then whatever value we set for the basis point.
Sure.
All right, so here it is in the context of the whole Bellman equation.
Mm-hmm.
So this is cool too, right? I just changed the order of summation and kind of regrouped a little bit.
Mm-hmm.
So now we've got max over actions, the reward of that action for the state that we started in. Now we're summing instead of over all next states, we're summing over just the basis points.
Sure.
We're multiplying some quantity times the value of the basis point. What can we say about this value here if we write it, let's say, like this? So we can write this as some function t of the state, the action, and the basis point. And the sum over next states is kind of already built in here, right?
Yes.
I gave this a name. I called it t prime, because I wanted you to see a connection between this and transition functions. So how is this like a transition function?
Well, it says, if you're in a state, you take an action. What basis functions will you go to next?
Right, which you don't. I mean, in the actual MDP, you don't go to the basis functions. But the point is that this acts like a transition function in that it's non-negative, right?
Mm-hmm.
And when you sum up over all SBs, over all the anchor points, it sums up to 1.
Right.
Why does it sum up to 1? Because this is a convex combination and this is a convex combination. And so when we combine them, we get a convex combination. We could do the algebra for that, but I don't think we need to. And so it acts just like a transition function. So we can actually fold the function approximator itself into the transitions. And all we get at the end of it is an MDP. So why does it actually do the right thing? Because MDPs have a well-defined unique value function, and that you can find it using things like Q-learning and value iteration.
That's beautiful.
Isn't it, though? So what we do is we end up with something that is actually a reasonable function approximator. It's taking the value of some state S prime and writing it as a combination of other states. And then we turn it into, over a series of steps, into a new Markov decision process over a smaller set of states, specifically over just the basis states. And at the end of the day, we know that this is going to be well behaved. We know that it's going to approximate things. Well, we don't know that it's going to approximate things reasonably, but at least without blowing up in a convergent sort of way, because we know a lot of stuff about MDPs.
That's kind of insane.
It's very clever.
No, it's very, very clever. So if I were going to, make too fine of a point on it, what would I end up with a kind of interpretation here? I'm like saying the MDP you're moving over is sort of from basis states to basis states.
Yeah, I think that's a good question. So it's as if we're going from a state to some next state, which is S prime. And then from there, we're making an additional mini transition to the basis states, the SBs. And the weights on these probabilities are the combination weights, are the convex combination weights. Convex combination weights look a lot like probabilities.
Right, they do.
So it's as if each time we make a transition to a next state S prime, we make an additional little transition to each of the basis states, and from there we continue. And so we can actually solve out what the value function is over everything by just solving the MDP over the basis states.
Right.
And then we can extrapolate that or interpolate that to anything that we want.
I love it. That makes some sense because the basis states sort of represent a set of states. So really what you're talking about is you're averaging over the set of states that kind of get aliased through the basis function. I think that's beautiful.
Yeah, exactly so. So yeah, we fold our function approximator into the MDP itself.
Done.
Poof. Very cool. So the good news is here's a value function approximator that is very well behaved. The bad news is it's hard to do some things with it because value functions aren't always very well represented as averager type things. There's often kind of weird cliffs and so forth in the value function that are not well captured by just smoothing everything out. But still, this is a really nice idea.
Beautiful.